Okay, we will be recording this part of the session. If anybody has any objections with recording, please say so now. Okay, thank you. Today is virtual background day, so I've got my Batman Gotham virtual background, and this is as a reference to our new addition to the family, who will hopefully arrive in a few months, little JD, as I will be calling him. Little JD is for Jorge Damian, and yes, Damian is because of Damian Wayne, the son of Batman. My wife is that cool that she's allowing us to name him Damian because of Damian Wayne, which makes me really happy. Okay, so right now we're on the topic of controllers and control actions. And we had just gone through talking about the proportional integral control. And just as a brief, very quick summary on that, the integral control, the proportional control is just going to do an action that's in proportion to the magnitude of the error. If there's a lot of error, there's going to be a lot of control action. If there's small error, small control action. And that can help drive the response of the system towards the reducing that error. But we're going to have the steady state issues that have to do with the type of the system. And so we incorporate now the integral component to make a proportional integral controller. And so what does the integral component do? The integral component is going to automatically add an S or a pole at 0 to the transfer function. That automatically is going to increase the type of the system. And therefore, it's automatically going to have an improvement on the steady state. That's the purpose of the integral control. And basically what the integral part is doing is that it's the memory part. It's looking at the past, at the accumulation of the error in the past. And so the proportional is looking at the present, or acting on what's occurring in the present. The integral is acting on the accumulated information, so it's basing its action on the past. And so now we're going to talk about the next type of control action, which is the derivative action, which is actually going to try to look at the future. Okay, so the proportional derivative action. So basically what's happening now is that we still have the error. We have the proportional action, which is one that's still going to stay there, the proportional action. And now we're going to be adding a derivative of the error as a part of the control action. Now, what is the derivative of the error? What would that represent? Well, a derivative of something represents the rate of change. It gives us a measure of the slope that at a certain point in the development of a curve. So the derivative can basically tell me how quickly a curve is either increasing or decreasing. So it's kind of giving me a measure of the rate of change. And so the derivative of the error is giving me a measure of the rate of change of the system. If we apply the Laplace transform to this and obtain the transfer function, well, the Laplace transform of Kp and the error is going to be Kp. And the Laplace transform of the error is going to be given by an S element that's going to be in the numerator, or that's going to represent a 0. So if we apply the Laplace transform, we get this transfer function here. In the case of the transfer function for the system, for the controller, I'm sorry, we usually identify certain constants that are going to be related to that. So in the basic form or the natural form of the controller, the integral controller, we defined a time reference TI. Here we're going to define time reference TD, and I'm actually seeing that there's an error in the slide, and I'm correcting that. The reference is TD actually here. And in the end, we're going to have this proportional constant that's going to be throughout. This is one representation of the ideal derivative control. We can actually reconfigure this in another way, but actually what's happening with a derivative control or proportional derivative control is that in the same way in which in an proportional integral control, we are adding an S in the denominator, an S at 0 or a pole at 0, we're adding poles to the root locus. In the case of the proportional derivative, we are adding a 0 because it's going to be in the numerator. Now, remember one thing, any sort of adding or incorporating of poles and zeros to the root locus is going to reconfigure the original system to a new representation that can help us comply with certain design criteria. Let's talk a little bit about that. So another equivalent representation of the proportional derivative controller is that we can factor the constants and just have one constant that we're going to call KD. And basically what we're going to be incorporating is that we're going to be incorporating a 0. We're going to be incorporating a 0 into the root locus at S equals minus Z, where Z is going to be a value that we're going to define. Now you're saying, well, wait a minute. We've been talking a lot about poles. And we know that the poles define the behavior of the system. We also know that the poles are going to define stability. So what use is there to add a 0? Well, in the end, anything I add to the root locus, either a 0 or a pole, is going to reconfigure the root locus because of the two rules that we mentioned, that any location in the root locus has to comply with the magnitude rule, and it also needs to comply with the angle rule. So adding any sort of pole or 0 is going to automatically reconfigure the root locus anyway. So even though a 0 doesn't really affect stability, we're going to see that it is going to reconfigure the root locus, and therefore it can reconfigure the behavior of the system, because it's basically going to be able to add new possible locations for additional zeros that can be additional poles, I'm sorry, that can be dominant poles for the function and change the behavior. Let's talk about this. So when the integral control action helped with the steady state error, the derivative action is going to improve the performance of the system with regards to the transient. And what are factors that have to do with the transient? Well, the setting time and the overshoot. Those are going to be key typical factors that are going to affect the transient. So while with the proportional integral, we're reducing the steady state error, we're going to play around with the derivative to try to control or try to manipulate the setting time and the overshoot. Okay, so let's assume that we have a transfer function, okay, that has, this is the original transfer function that we're looking at. This is the transfer function for the system. And I'm going to be adding proportional derivative controller. And what does that mean? It means I'm just adding in the numerator something that looks like S plus Z. I already have a constant here, K, so the derivative constant is kind of absorbed by that one, and I still have a constant K. I want to add something in the numerator with that model. So we're looking at 3 examples here where I'm adding the S plus Z to the numerator. I'm adding it, and I'm adding 3 different configurations for this. So I'm adding one that says S plus 2. I'm adding another one that says S plus 3. And I'm adding another one that says S plus 4. And what do we notice here for each of these 3 configurations? So again, I'm just adding a 0 here. S plus 3, S plus 2, S plus 3, and S plus 4, and seeing how it behaves. Well, I'm looking at the dominant poles. I'm looking at the values of K for a certain behavior. Okay. What is the reference behavior that I want? The overshoot. The overshoot is what I'm looking at here. The overshoot is what I'm trying to achieve. So the overshoot, I want it to be 25.38. This is the design parameter for the 3 configurations. And the overshoot is going to be directly related to the, dampening ratio. So an overshoot is going to be directly related to the damping ratio. Okay. Can somebody tell me, look at the columns. For the 4 systems, we have different values of K that give us the same overshoot. But can somebody tell me what is the difference between the reactions of the systems? Where I'm seeing the change while adding the derivative component? Look at the columns. Can somebody tell me where? I have my screen here minimized, so I don't know if anybody's raising their hands. Can somebody tell me where are you noticing an improvement in the system response? Anybody? Look at the values in the columns. If the overshoot is the same for the 4 of them, but where am I noticing a difference? In what other parameters? Daniel, shoot.
What was the name of the, under the damping ratio? That was the
natural frequency.
Yeah, the natural frequency.
I mean, see a different. Go ahead.
No, I don't know if that's, I mean, an improvement, like, you know, having different frequencies, but that's a value. I mean, every other value is changing as well, but I don't know if it can be counted as like an improvement.
Well, it's a good observation, Daniel, because it is different, it is changing. And remember that the natural frequency, remember that when we have an overshoot, and I'm going to show the graphs in a minute. I just want you to sort of visualize this. You guys, so it's a good observation, Daniel. It is different, and it is going to be affected by whatever I'm adding, because the overshoot is going to generate a natural oscillation. So we do have to be mindful of that. So that is changing. That is a good observation. Pablo, you also have your hand raised.
Yeah, I'm not sure if T means time. Is it?
Yes.
Yeah, so I see that time is like lower. So maybe there's something there.
Yeah, that's the ticket here. So remember these. This is the setting time and the peak time. So what's happening with the setting time for the 4 configurations? It's changing, right? The original setting time was almost 4.3 seconds. And then for the first compensation for S plus 2, the setting time got reduced to 1.33 while I maintained the same overshoot. Remember how it's kind of elastic? If I try to reduce the setting time, the overshoot is going to try to get larger. But with the compensator, I achieved a reduction of the setting time without affecting the overshoot. However, the natural frequency increased. So it's going to oscillate a little bit more. And I can see over here that the setting time gets a little bit larger here and even larger here, but even with the fourth compensation, it's still lower than the original. And the difference is that with this one, with the compensation D, I don't get as much oscillation. So I am improving the response. And the peak time is also improved. So from having a peak time where the overshoot occurs at 1.46, almost 1.5 seconds, I can reduce that up to 0.46. So adding that compensator is automatically improving somehow the transient response. Okay, Daniel, you still have your hand raised. I don't know if you didn't lower it or if you want to ask a question. Go ahead. Please.
No, my bad.
Oh, okay, that's fine. So you see, adding that 0 with a certain value, s plus 2, s plus 3, and s plus 4, and we're going to talk about a little bit about how to add that value and how to tune it. We're automatically improving the system. Okay, we're automatically improving the system response. And so actually what's happening, the notes here on the bottom is the following. Some of the simulation parameters that we use and comparison parameters are with regards to the canonical second order representation of the system. And so the only thing that we're noting here is that we can approximate the response to a second order. There's going to be certain situations where the response cannot be approximated to a second order system. Meaning if I take these values, the dampening and the natural frequency, and I represent these as a pure second order system, and I compare the response of this system, which is not second order, I'm sorry, we're going to notice a difference. Okay. Okay. Questions up to this point before we jump over and look at a few other things.
No.
Okay, good. Thank you. So now what are we seeing here? The only thing we're seeing is how the root locus is changing according to each of these configurations. So we're noticing how the root locus is different, okay? And this is the root locus for the uncompensated system, the first one. For the rest of the compensated systems, we can see them there. Now, notice that there's a line here. I want to talk a little bit about this line. There's a line here that says 0.4. Remember something I said. The overshoot has a direct relationship with the damping ratio. So for a particular overshoot, there's a direct damping ratio related to that. And if we want to mathematically calculate that, we can. There's a formula we saw in the second unit that gives us these relationships. It's directly related, the overshoot and the damping ratio, directly related. And so in the root locus, there are going to be these lines that define the damping ratio. And so this is the line that defines the damping ratio of 0.4. So any root that is located within this line is going to comply with the 25.38, 25 point something overshoot. However, maybe what's happening actually is that this particular point that is right now the uncompensated system does comply with the overshoot. However, it isn't complying with it doesn't have a very good response time. And so to have a better response time, we need to move this point, move it a little bit more towards this side. So what do? We need to reconfigure the root locus to do that. Adding the 0 changes the dynamic of the root locus and is helping me move that point. Now, I want to show you something here in Matlab that's actually very useful. And I'm gonna switch over to Matlab. Can you see Matlab? PowerPoint, Matlab, PowerPoint. Is everybody seeing the switch?
We can only see the PowerPoint.
Oops, oops, let me do that again.
There you go.
PowerPoint, Matlab, is that okay?
Yes.
Okay, so let's do this. I'm gonna do the root locus for the uncompensated system, which is this one here, first one. This is the uncompensated system, right here. I'm gonna do the root locus for that one. And remember that the idea is for you guys to be able to practice this also as well in Matlab. We're gonna be doing the lab exercise 3 has to do with you applying the root locus and doing this. And we're gonna be doing another lab exercise for that, for this topic also. So I'm gonna say sys, what is that, sys 9.2. Sys 92 is equal, let me change my keyboard here. Is transfer function of, I'm going to do the uncompensated one first. Transfer function of 1, comma, the convolution. You know what I'm going to do to simplify things? I'm going to call it, since the denominator is the same, I'm going to call it, I'm going to do a denominator sys 92, which is going to be just a denominator, so I can reuse that. Whoops, let me do a clear all and a CLC. I'm going to do a den conv, I'm sorry, den sys 92. This is going to be the convolution of s plus 1, s plus 2, and s plus 5. So it's going to be the convolution of s plus 1 times the convolution of s plus 2 and s plus 5. Boom, boom. That's going to be the denominator. Remember, you can follow along in your MATLABs if you wish. And so so I don't have to replicate this. And so I'm going to say sys 92 uncomp, which is the uncompensated one, is going to be the transfer function of 1 and den sys 92. Okay, that's going to be the first system. Okay, and I'm going to do a root locus of that one. Sys, oh, I said sys 93. No, sys, do that. Sys 92. There we go. I'm going to do a root locus of that one. Sys 92 uncomp. And look at the root locus of the uncompensated system. This is the root locus of the uncompensated system. This is the same as I was showing in the PowerPoint, just that this is the MATLAB, maybe prettier version, but it's the same one. And so I want to show you something here in MATLAB. Remember that we can walk along if we want, we can kind of walk along and look at values. So we can look at the damping and the overshoot. The damping and the overshoot are related. So we can do that. But there's something interesting here in the root locus. So you can always have the opportunity to, when you do a plot, to put the grid. But the grid that we're being given here is a different sort of grid. It's not a grid with regards to X and Y. What do you think these values are? What do you think these lines represent? What are they? Oh, that's a horrible line. What do these lines represent here in this grid? Daniel, go ahead.
The damping ratios.
Correct, Daniel. These are the damping ratio lines. So that can really help me play around with the root locus, because I can, basically what I need to do is that I'm going to clear this and I'm going to do a zoom. Basically what I'm trying to do with the controller is that, I'm going to focus here. I know that the overshoot needs to be around 0.4. So I'm sorry, the overshoot needs to be less than 25%. So the overshoot for 25% should be 0.4, which is between 0.42 and 0.58. So I know that I have to look between these two lines. By the way, the relationship of overshoot and damping ratio, you can find that you can find that formula in Unit 2. We saw that formula. But actually, you can just even Google a table that can give you the relationships. It's not, you don't have to calculate it always. It's a fixed relationship between overshoot and damping ratio. And so I know it has to be between these two lines. So I can kind of zoom here even more. And so that can actually help me look, right? So I know it's going to be between, it's actually going to be between 0.4 and 0.3. So I can actually look between these lines. And I know that the damping ratio of 25 or 25 point whatever is going to be between these two lines. Now, notice something here. I'm also given the gain and I'm also given the natural frequency in the pole. So I can take this value, for example, what was the value? The value was 25.38. I can plot the step response, and I can see I have a setting time of 4.26. Maybe that's not good enough, and I need to move this root over to this side. I need to change the root locus. How do I do that? I can do that in two ways. I can add another pole, or I can add another zero. Okay, either one is going to reconfigure the root locus. So now let's look at the one of the first compensated systems. So I'm going to say that I'm going to call this comp A. Compa is going to be, the compensation for A is 1, 2 in the numerator, I'm sorry. And so now let's do the root locus of that one. Compa. Sys 92 compa. Wait a minute, I did, how did that come about there? Oh no, yeah, that is the one. It looked weird, but it is the one. Oh, let's see. Let's see if you've paid attention, kids. That root locus is a cross, isn't it? I mentioned before in class that the root locus for crosses occurred with specific types of systems. What systems gave me a cross as a root locus? Does somebody remember? Of course not. When I'm recording, nobody remembers. The root locus of a cross is going to be given by second order systems. Second order systems, pure second order systems are going to give me a cross. It's a very simple root locus. Can somebody tell me why this happened when I added this compensator in the numerator? I'm going to switch over here to try to visually help you guys out. Oh, by the way, it's not A, it's B, actually. It's not compensator B. Let me just do that for the purpose of, I'm going to give you time to think. It's not A, it's B. So we're going to call it syscomp B. It's not A, it's B. Just because there we go. I gave you enough time to think. So only a pure second order system is going to give me this cross as a root locus. Why is that happening with compensation B when I added the derivative control? Pablo, shoot.
I'm guessing simplification, like S plus 2 multiplying K, and there's also an S plus 2.
Correct. So notice what's happening. By adding the compensator, I'm mathematically eliminating this component. And what's left are these two that give me a second order system. That's why it says here on the bottom that it's a pure second order system. Okay. And now the root locus, if I go back here and look at the root locus, I can do a grid also here. And notice what happened. The point that I originally had over here around the 0.4 line automatically moved to the left, drastically moved to the left. So that's why we see a great improvement in the response time, in the response time, the setting time. Okay, so adding that compensator to the system in the form of a 0 is going to drastically change the root locus and give me different configurations where the poles are moved. Now, let's just quickly look at the other ones. If I do the compensator B, which is S+3, I believe. No, this was actually C. I'm making a mess here with the. Let me just do this. This is going to be called C, compensator C. If I do, let me just, no, I put the two. No, okay. Wait a minute, I'm making a mess here. This is B. Okay, it's 1 and 2. Now we're going to do C, and C is going to be 1 and 3. Okay, and let's look at the root locus of C. And so the root locus of C has also moved the pole, but it hasn't moved it that much. It hasn't moved it that drastically. Okay, if we don't want to affect other factors. And lastly, if we do the D compensation, which is S+4, we're going to say it's very similar to the other one. Okay, it hasn't moved it that much, but also it's changed the root locus. And notice that the original root locus was kind of like a cross, and once we added the new 0, it kind of flubbered up and got this little bump here. Again, that's the movement of the root locus that's changing the position of it and the position of the roots, and therefore the position of where they intersect with the grid lines that have to do with the damping ratio. And in the end, that damping ratio is going to affect the overshoot. And it's also, in the end, it's affecting the transient response. Okay. And that's basically what we're trying to do with the response of the system. Lastly, if we graph the functions, if we were to do a step for each of these, we would see that each of the systems has different responses, okay? Different responses and response times, okay? Okay, so, so this would be the response to the, oh, give me a moment. Oh, no, okay, I thought I wasn't recording. So this would be the response to the system. Give me. Okay, there we go. Okay, so these are the responses. I'm just going to do these here in Matlab just so we've got them. What I just did there is that we've got each of the systems, the uncompensated system. I'm going to do a clear all here. I'm going to do a clear screen, not a clear all. Clear the command window. Okay, so we've got the uncompensated system, we've got compensation B, we've got compensation C, and we've got compensation D. So the only thing I'm going to do here is that I'm going to do a step. I'm going to do this in a whole bunch here just to, I'm going to do the step of the feedback of sys 92 uncomp, comma 1. And the feedback, remember that we're using the forward transfer function. So that's why this is the feedback of sys 92 comp b, comma 1. I want to put all of them on the same graph. Feedback of sys comp 92, I'm sorry, sys 92 comp C, comma 1, and the feedback of sys 92 comp D, comma 1. There we go. Okay, and that should give me the graph of the 4 responses in the same graph. Okay, let's see what happens. I just want to check that I don't have any other plots open. Okay, good. Now let's run that, see what happens, see if we don't break Matlab. There we go. We've got the 4 types of responses there. Okay. So let me check something here. What I'm not checking there is that. Oh, I'm not putting the. I'm sorry. I'm not putting the case. I'm not putting the corresponding case. I'm sorry. Remember that we did this for a specific. Let me close this one. Why didn't this? So remember that for each of the situations, we're looking for 25.38. So each of the cases has a different case. So I'm going to write those down. So I'm going to write this down again. For the first one, it's going to be, K is going to be 23.72. So it's going to be 23.72 times the uncompensated one. For this uncompensation B, it's 51.25. So it's going to be 51.25. The third one is going to be 35.34. And the fourth one, or D, is going to be 20.76. Now, another reason for doing the different configurations is that maybe our compensating variable to K, maybe we get a value of K that mathematically gives us the response we want, but maybe physically our component can't give us that value. So that's another reason to be able to have this sort of margin to maneuver. There we go. That's it. So these are the 4 responses. So the uncompensated one is blue. So we're going in order. The uncompensated one is the blue one here. Uncompensated, I'm just going to put a U there. The red one is compensation B. Then we've got light brown and purple. Then light brown, which I actually think here that the light brown is what they call yellow here. Seems yellow to me. Seems yellow to me. This one would be C. And the purple one, which would be this one, would be the D. And so we have the different types of responses there for the system when we've added the 0 there, the derivative control. Okay. So now we're going to see another example. Okay. If there are any questions with with this one. I'm going to close this graph. Come on, jump over here. Pablo, please go ahead. Oh, I closed the window. Let me
Yeah.
run that again. Yeah.
Yeah. So I was gonna ask. I think it's C. It looks like it has a bigger peak. Is it still the same overshoot regardless?
Yeah, the thing is that it's less than 25.38. So
Okay.
remember that when we're talking about the overshoot, we're kind of, the parameter is a 25.38 or rather 0.4. Actually, the way this problem was defined was with regards to the overshoot, but the definition was we want a damping ratio of 0.4 or less. So it's with regards to the overshoot, if you're not given a setting time, remember that the overshoot, we're always aiming for less than the value, okay? So at least
Okay.
less than the value.
Okay.
As long as it's less, then we're okay. Okay, good question. Thank you. Okay. So now let's assume that we want to design a proportional derivative controller that's going to yield a 16% overshoot or less. And a setting time. We want to improve the setting time. We want to improve the setting time to at least 1/3 of the original. 1/3 of the original value. Okay. So first off, let's look at the uncompensated system, which is the one we've got here. So let's jump over here to Matlab. I'm going to do a CLC. Clear all. I think the CLC eliminates. There we go. And I'm going to define this system. I'm going to call this sys93. Sys93 uncompensated. And this is going to be the transfer. I'm going to do the same thing with the denominator because we're going to be repeating it. So I'm going to call it den 93 convolution. Let's just call it den 93. This is going to be the convolution of 1 and 0 times the convolution of 1 and 4 and 1 and 6. That's going to be the denominator. We're going to be using that one. And I'm going to call sys93 uncompensated is going to be the transfer function of 1. We can just leave a 1 there. 1 comma den 93. So this is going to be the uncompensated system. Okay. And I'm going to do a root locus of this system. Oh, so first off, let's do a step. Let's see how the system behaves. So we're going to do a step of the feed. Well, rather, we're going to look at the root locus first to look at the design parameter. So it's going to be sys93 uncomp. And we want an overshoot that's less than 16%. So I'm going to leave it that way. I'm just going to do a zoom here. So if we look at the root locus, and I've already got this solved, but we can just look around here. So if I want a 16% or less value, so we're around here. So we can look for it here in Matlab. So for example, for 15.9, this is fun. My pulse is really not good on those things, but it's fun. I'm gonna leave it at 15.9. I actually have the value here in the PowerPoint. It's 43.35. Okay, so K is 43.35. We can see it here on the graph, 43.3. So let's go with K is going to be equal to 43.35, 43.3. And I'm going to do a step just to see how the system behaves of feedback. Oh, I'm going to call this K uncomp. Okay, just to differentiate. And I'm going to do a step of the feedback of K uncomp times sys 93 uncomp, comma 1. Okay. And see how the system behaves. And so this is the system characteristics. So the peak response right now is that overshoot is less than 16%, so we're fine there. But the setting time right now is approximately 3.47. So I want to reduce that setting time to at least 1/3 that. So if it's 3.47, 3.47 divided by 3, this will be around 1.15. This is what I want to reduce the system to. So what we're going to be doing is that I'm going to be adding some controller. So if I add, the theory is if I add a proportional derivative controller where I have as s plus z here on the numerator, I'm going to be able to along the same line of damping ratio, I'm going to be able to get a better response. So the thing is to define this value of z. Now I'm going to do this kind of in a tuning method. So if you notice what we did in the other one, there's a range of roots that we have here that go from 0, or rather from 0 to -6 or -6 to 0, going by 4. So in the other one, notice that it was from 0 to -5. And so we gave it values of 2, 4, 2, 3, and 4. I'm going to give it just some values to kind of play around. So I'm going to give it a values of 2. I'm going to play around with the values of 4. I'm sorry, 4 is going to cancel it out. I'm going to give values of 2, 3, and 5 to z. Let's see what happens with those 3 values. Okay. And I'm going to call these B, C, and D, just to see what happens with those. So what I'm going to say is that sys 93 comp B is going to be equal to the transfer function of, I'm going to say that that's going to, for B, I'm going to say 1 and 2. I'm going to give it a value of 2, and I'm going to use the denominator, 93. I'm going to define them all together, and we'll see them all together directly. I'm going to do syscomp A, and I'm going to give it a value of 3. And I'm going to do, what did I do? I did A. No, I'm sorry, C. C is going to be a value of 3. And D is going to be a value of 5. And we can do 3.2, 2.3. We can play around with those values. I'm just giving them whole values just to kind of prove a point here. And I'm going to do the root locus of each, just so we can compare them. So I'm going to do the first one, root locus of sys 93 comp A. I'm going to do both so we can compare them. I'm going to do the root locus of the uncompensated system. This is going to be sys 93 uncomp. Then I'm going to do another one, figure of the root locus of sys 93 comp B, which is with the 2, I believe. And let's just see how the root locus is, the root locus changes. Did I get the 2 graphs? Yes, I did. So this is one, and this is the other one. Notice how the root locus moved to the left. It moved drastically to the left, adding the 0, and it changed the literal, its behavior. It's kind of trying to be a little bit more close to the second order. Okay. Let's do the C. Let's do the root locus of comp C. I'm going to keep the other one so we can compare it. It looks the same, but it's been stretched a little more. So it's giving me a little bit more range of values on this side. Oh, something that we didn't do. I forgot to do this. For comp B, which is this one. Let's look for the approximate value of K. So in this one, we had the grid lines here. Let's use the grid lines to kind of help us out. And let's look at this part here. And let's look for the 43 point, the value that we were looking for, which was around 33. Which was it? Let me just check the value. It was, what was the value of K? 43.3. Thank you, Carlos. 43.3. So the 43.3 was just along or between, it was between the 0.56 and 0.42. So we've got a damping ratio of 0.507. So what am I doing that? I'm just so we can narrow down. So it's 0.507. So it has to be in this range here between these two lines. Okay. So I'm going to do a zoom there. I'm just going to grab an approximate value. Okay. And I'm going to go here to so we're looking for 16. Oh, right there. So the gain there is 58. So I'm going to write that value down. So K comp B is going to be 58. And we're going to compare the responses. Okay. Now I'm going to close this one and let's look at comp C. So comp C is this one. This one was with the 3. We're going to put a grid here. So it has to be between, again, these two lines. So I'm going to do a zoom there. There we go. And let's see what we can find here. So there we've got a 47.6. So K compensator C is going to be 47.6. And lastly, let's do compensator D. I'm going to close this one. I'm going to tell you an anecdote right now. I would love to go back in time because of the following. When I studied this in school, remember I'm an electronic cybernetics engineer. When I studied this in school, we didn't have Matlab to do this, by the way. We had Matlab, but Matlab didn't, I don't remember Matlab having these tools, or we didn't use them. I don't remember us using them in class. And so now, I'm sorry for going off topic. It would have to be between this line and this line. So I'm going to zoom there. We didn't have Matlab to do all this, so we had to kind of trace the root locus by hand or manually, which is really not fun. And something that I have a takeaway from that is that we took so much time drawing the root locus by hand, plotting it, that we really didn't take enough time to analyze what we were doing. And so we didn't take time to analyze and compare. We didn't analyze, we just did things mechanically. And that's something that we need to change. So we didn't have enough time to do analysis because we were taking so much time trying to do the drawing. So there now we have 23.5 for this one. So I'm going to say K comp D is 23.5. Okay, so now we've got the three alternatives. And again, I just said 2, 3, and 5 because these were values along the range of the poles. But we could go even deeper and say, okay, I noticed that with the 3, it's with the good behavior. Let's do a 3.1, 3.2. We can play around with these, okay? I'm just trying to kind of demonstrate how we can use this to do design. Let's look at the 4 responses to see what happens. So I've got this jumble that I wrote down here. I'm gonna modify this. It's always a problem when I try to do copy paste because it's not. So it's gonna be, I'm gonna do the steps of all of them. K uncomp times SIPS 93 uncomp. K comp B times sys 93 comp B. Copy pasting is really dangerous, kids. Hope I don't make a mess here. K comp C, but it's being recorded so you can look at it there. And then K comp D times sys 93 comp D. And let's look at all of those graphs together and see which one looks better. There we go. So let's make this bigger. So let's look at these 3 graphs. So again, I think it's the same dark red, blue, red, yellow, purple. So blue is the uncompensated system. We're less than the 16%, but it might be a bit slow to respond. It's slower to respond. Then we've got the red one is compensation B with S plus 2. Okay. And then the brown or yellow in this case, I see it yellow, is compensation C with the S plus 3. And then the purple is D with S plus 5. Now, what was the parameter we were trying to improve? Somebody remember?
The setting time?
Setting time, correct. We wanted it to be
3 times.
What is that background that's moving around in your background? It's like it's somebody in space in sort of a lava thing. That's a spaceman. That's kind of cool. We want it to be at least 1/3. And remember something when we're talking about control system design, when we and it goes back to Pablo's question, when we're talking about an overshoot, a setting time, and you say it's 25% or 1/3, it doesn't mean necessarily exactly that value. It's at least less than that value. So let's look at the steady state. No, I'm sorry, not the steady state. Let's look at the setting time responses for the 3 systems. So the original system, the setting time was 3.47. For the red system, it's 1.22. What was the target? It's 1/3. It's 1/3 of 3.47, so it's 1.15. So the red system is 1.22. We're a little bit overboard. The yellow system is 1.15. So I think we're good there. And the purple system is 1.7. Which one would we choose that complies with the parameters?
The
B, C,
yellow
or D?
one.
Yellow.
The yellow, which is C. And which of the compensators was C? The compensator in C was, no, it was 3, actually. Remember we did.
Oh yeah, 2 was the one that.
Yeah, so we did 2, 3, and 5. So 2 was B, 3 was D, C, I'm sorry, and 5 was D. So 3 would kind of work. We can go deeper and say, okay, let's see what happens with 3.1, 3.2, 3. We can go even finer or deeper. But notice what we're doing, we're tuning. This is what, if you've ever heard of the concept of PID tuning, this is what tuning means. It means kind of adjusting to get the parameters the way we, in general, the way we want. Okay. System, this one here, I'm going to erase the other ones. This one here where we have, which is compensator C, which was for S plus 3, or rather we're adding the 0 at 3. This is the one that kind of complies with what we were looking for. Okay. We might find a value between 2 and 3 that makes this even better, because 2 goes overboard. 3 is right kind of on the edge, so we can maybe play around with that. Between 2 and 3, we might get a closer value. Okay. Rather, I'm sorry, not between 2 and 3, between 3 and 5, because no, well, any sort of value around 3. I'm sorry, any sort of value around 3 is gonna give us a value that we can work with. Okay, so that's kind of what we were doing now with this. We were kind of doing some tuning. Okay, and the whole explanation of this is also in the PowerPoint, but it's not with the Matlab. It's with the graphs from the book. Luis, go ahead. You got a question, please.
Yeah, is there any way to like pinpoint what value we need to get there so we have like the perfect, I guess, solution, or is it just like really tuning and tanteo?
No, you can do the pinpointing, and let's talk a little bit about how we would do the pinpointing. And I'm going to go to the root locus, and I'm also going to explain. Your question is a very good one, Luis, and I'm going to answer my version of it. So we can do the pinpointing, and so let me go back here to the. I'm gonna remove these here. Your drawings, this, I'm going to close this up. So I'm going to go over here to the root locus, the original root locus, the uncompensated one. I'm going to do the uncompensated. This is the original root locus, and this gives us a certain response. Okay, and this is the original system without any sort of compensation. Okay. I'm gonna go, give me a moment here to look for it. I'm gonna go over here to, just give me a moment to open it here for a moment. I'm gonna go to unit 2. And I'm gonna go over here. What's it? Okay, here we go. I'm going to show this one. So remember that we have a general representation of a second order system that's got these parameters, Wn and theta. Okay. And so we have these mathematical expressions that come out of solving the differential equation for a particular system of second order. When you see in Matlab the damping ratio, the Wn, et cetera, it's basically applying these formulas. Okay. And so you can, and remember that even these formulas are approximations because they come from interpolation. So Luis, what you would do is you want a setting, the original setting time was 3.40 something, right? And 1/3 of that would be 1.15 something, right? You would go over to this formula here, okay? And you would set the setting time to the value, which would be 1.15. For the overshoot that you want, you can find the values of so with this formula and this formula, you can have a 2-order system and find the damping ratio and the natural frequency. Okay, are we okay up to that point? These are mathematical calculations that you could do, right, Luis? And the rest of you, are we okay up to that point? We could use these formulas to find those values, okay? So now we go back over here. And so those values are going to give you values along this grid that we just showed you. And those values are actually going to give you a coordinate. The values are going to give you a coordinate around, I don't know, here. Okay, are we okay up to that point? Well, so this coordinate actually has an angle. I'm going to call this theta. And it has a magnitude that has to do with these values here. This is just simple Pythagoras. Are we okay up to that point?
Yes.
The root locus has properties. The root locus in its properties, and let me open the other, give me a moment here. In its properties of the root locus, in the properties of the root locus, there are these two properties. Any point in the root locus has to comply with the magnitude rule and the angle rule. So if you substitute that coordinate into the transfer function and do these mathematical calculations, you can find the value of k that gives you that coordinate. And that can help you reconfigure the root locus. So you can do all of that mathematically, okay? And it's just a bunch of, it's a series of procedures. The fact is that in reality, what you want is the system to at least have less than a 25% overshoot and less than 1/3 of the original setting time. You're actually not speaking of these precise values, you're talking about ranges. So in reality, and I'm sorry to say it this way, but in reality, what we do is that we do PID tuning. That's what we do in reality. We look at the origin, and actually the guide that I'm going to give you that comes from the textbook has to do with this PID tuning, and the guide actually tells you this. First, look at the uncompensated system. Look at the type of the system. If the steady state isn't what you want, then just add a 0 that's very, very close to the origin, and that's going to include the steady state. That's the integral part. Test it. See how it looks. Did it improve the steady state? Yes, perfect. Now look at the parameters that have to do with the overshoot and setting time. Add a differential controller that's around the range of the poles. Look at the behavior. Is it improved? Look at it, what percentage it's improved. If it's not improved enough, then move the 0 around a little bit. And do that in an iterative manner until you kind of get within the range you want, okay? So you can do the precise calculation. It's gonna take you much more time than probably just using the tools you have to do the tuning. And actually in real life, and again, I don't know how many of you have used PID controllers, maybe with the Arduino, or have had to interact with a PID controller in real life. It's basically the KD, KP, and KI that you're just adjusting certain values to. And as long as you know how those are defined and understand this, you're going to be able to set the values by tuning. If you don't understand what you're doing, basically you're just going to be moving the constants, and you're going to be adjusting one thing and moving another, and everything's going to be made a mess. Okay. So does that kind of answer the question, Luis? Yes, we can do the precise calculations, but in the end, the result is probably going to be the same. with much less effort than using the tools, the mathematical and computational tools that we have. Okay. And we're going to do some exercises where we're going to be a few more exercises and actually another lab exercise next week where we're going to be doing the tuning. Okay. So is that okay? Did I answer the question, Luis?
Yeah, you did. Thank you.
Thank you. Okay. So let me close this up. So the next thing that we're going to be talking about is we're going to be talking about how to put everything together and talk about the PID controller, which is actually going to be the combination of the three controllers and see how we can do the tuning of everything.